Hi, today we are going to talk about WebGPU and generative AI. That's also equals to almost magic. So this talk we are going to talk about on-device generative AI and building your own stability diffusion for us, the Dall-E in your browser, and how WebGPU brings into the equation. So first, who am I? My name is Rabimba Karanjai. I'm a Google developer expert in web technologies, and I used to work for WebXR, and that's how I'm very much interested in WebGPU. So what we will be covering today. So why WebGPU is being developed, some of the comparisons between WebGPU and WebGL, and why WebGPU is efficient, deeper dive into the concepts and some of the features. First, let's talk a little bit about WebGL. WebGL has been incredible for enabling widespread distribution of real-time 3D content, use cases we couldn't have imagined when the API was first under development. The fact that it's available on every major browser and every major platform makes it an incredibly compelling way to deliver rich content to a huge range of users. But it's also definitely showing its age. WebGL has been web's GPU API for over a decade now, and the API it's based on is significantly older than that. OpenGL itself was released nearly 30 years ago, and it is showing its age. Real-time graphics have evolved in these 30 years, just a tiny little bit. By the way, the hardware needed to produce the image on the right costs almost 2,000 to 50,000 in 1993. The hardware needed to produce the image on the right now is roughly $500 if you buy from local Target, and even less if you shop for bargain in Black Friday. In order to keep up with increasing hardware capabilities and developer demands, the APIs that drive GPUs have evolved to keep up. They have discarded patterns that made sense a few decades ago in favor of APIs that more closely mirror how the underlying hardware works, which allows developers to take better advantage of it while allowing the graphics driver to be simpler. Unfortunately, WebGL can't really keep up with these modern APIs. So while it served us well, the various browser vendors have recognized for a while that we'd need to move on to something new. And thus, we have now WebGPU, which takes the best parts of the modern native APIs and exposes them in a web-native, developer-friendly, high-performance way. What are the new features we're talking about? Well, when I say new features, they are related to WebGL 2.0. So we have compute shaders, indirect drawing, render bundles, which I am going to talk about a little bit later, external textures, more flexible integrations, and of course improved debugging features, which is hugely beneficial. So some of the demos we have here is on the left, we have the Meet Skyball, which I'll link later so that you can take a look at the demo and also its performance and the source code. On the right, you have Spooky and the demo we all have been waiting for. Here, it's running a stability diffusion model completely in browser. It's loading the whole model in browser, and after that you can generate the prompts. Right now it's running in a MacBook, and you can see the image. But you don't have to just see it, you can actually also try it right now. This is a little experiment I cobbled up. You can actually use that to generate any kind of image. These are all relatively small 512 into 512 images, and they are cached into your browser session every time you open this page. If you want to play with it, just scan this QR code or go to this URL and you should be able to visit that. There is, however, a little bit of catch. You still need a GPU with 8 GB of VRAM or an Apple M1 or M2 Mac. The M1 or M2 Mac still has 8 GB of unified memory, so though it will work, it will still be a little bit slow. Quite a bit slow, I would say. It probably takes almost 2-3 minutes to produce an image, even that after loading the model, which takes its separate own time. But for our example, we are gonna ignore that. Also, even though it is running on a browser, it is running on a machine, it is dependent on how much powerful machine you have. So back to WebGPU. Why WebGPU, not Web Vulkan? Well, for starters, if you're familiar with API like OpenGL and go looking for examples of Vulkan or even DirectX D12, online, they can seem a little bit of daunting. It's pretty intimidating and it is a complex API. When I say complex, this is not even an exaggeration. The Vulkan source code can be really huge. I really wish that was an exaggeration, but it's not. So if you look at the source code sizes, you, you see the DX9 and DX11 were relatively slow. DirectX 12 is pretty big. OpenGL 3 was small. Vulkan is even bigger. How bigger? Yes, it still was going on. Aside from the complexity though, there are simple differences, set of goals between a web API and any native counterpart it might have. A web API is supposed to be safe, period. It should not have any undefined behavior, no access to user data unless explicitly verified, no access to memory, and it should be very much backward compatible. Native APIs do not have to abide by the same rules always. WebGPU is explicitly built to serve the needs of the web platform. It exposes only the bare minimum common features. It leverages underlying modern native APIs and much more web-friendly. For our example though, we used Apache TVM. So in Apache TVM, for our modern traditional workflow, what we have is we have model, we have manually write the compute shaders, and we have the app. For TVM, what we do is that we do the compilation via TVM. So for us, what happened is that I took the whole model of Stable Diffusion, generated through TVM the web runtime which we used. For our architecture, this is kind of how it looks for the generative AI part, for the Stable Diffusion part. So we're not going to go into deep into that. This can be topic of a completely separate whole talk of its own. Right now we're going to just use it as a tool where we input these models. We get a JavaScript runtime which we're going to use in our application, which is going to utilize WebGPU. For here we have the Stable Diffusion JavaScript, and that's what we can use for the WebGPU. Now going back, just look at a toy example. So this is a hello triangle code for both WebGL and WebGPU. I'll drop a link to this later. This allows us to keep the complexity of WebGPU to a minimum, so it's not too much more code than WebGL, and it is significantly less complex than the native APIs. Let's look at a comparison between how WebGL and WebGPU accomplish the same with a simple task. Drawing a single triangle. We're going to hand wave over some stuff for now, but we'll come back to it later. The first step for both API is to get the main object that you will be interacting with. In WebGL, it's a context. In WebGPU, it's a device. And right out of the gate, WebGPU looks more complex. But in this case, the added steps provide a lot more flexibility. For example, rather than the WebGL model of a context being permanently associated with single canvas, in a WebGPU, a single device can render to multiple canvases or none at all. Buffer management looks pretty similar between the two APIs, with the biggest difference being that WebGPU takes in a size and usage for the buffer at creation time, which are immutable afterwards. And also notice that we don't bind the buffer we want to operate on. We just pass it as an argument. These are patterns that you will see repeated throughout the API. For shaders, the big change is that WebGL uses GLSL and WebGPU uses a new shader language called WGSL, which is designed to cross-compile nicely to the various backends' preferred shader variant. Note that WGSL, the fragment, the vertex shader can be part of the same shader as long as they have different function names. This can be very convenient. There is no separate program in WebGPU like there is in WebGL. The shader program is linked as part of a much larger object called pipeline. The pipeline includes a lot of information that is set as bespoke state in WebGL, which is why it appears a lot more complex here. We'll dig into that in a bit. Finally, we get to drawing again. WebGPU looks more complex, but that's actually deceiving in this case. We are more explicit about setting up our rendered target, whereas WebGL there is a default one. But during the actual rendering, WebGPU avoids setting up the vertex attribute layout because that's part of the pipeline. Now, if you want to kind of play or build your own WebGPU app, just scan this QR code or go to this URL. This is a glitch site, so you'll be able to remix and play with the code. Play with the code, remix it, understand some of the concepts we have already talked about. Come back later when you're more comfortable about it. The benefits of an online video recording is that you can always pause it, you can go play with the code, and you can actually come back. Now moving forward. Looking through the previous code snippets, there's a lot that looks pretty similar. So how is it that WebGPU is supposedly so much more efficient than WebGL? Let me explain with sandwiches, because why not? Yeah, I know, stick with me on this one. So imagine WebGL is a sandwich shop. Every day you walk in and order the same sandwich from a waiter. The waiter passes your order off to the kitchen. But the situation in the kitchen is complicated. The chef speaks a different language than you ordered in. The ingredients are laid out in a confusing way. Certain sandwiches have not been delivered to health codes. Obviously, this is a lot of responsibility to put on the waiter. The quality and the speed of the translation and reordering skills become one of the biggest potential bottlenecks in your sandwich experience. Also, in case you missed it, the waiter is the graphics driver in this scenario. Then one day, the WebGPU Dall-E opens up next door. They have a weird rule. All orders must be submitted to the front clerk in advance. Once your order has been approved, they will inform your sandwich will be known as number 53. That feels like a little bit too much overhead for a single sandwich, right? But the next time you come in and call out 53 please, and your sandwich is done in a record time. So what's happening here? But plot twist, guess what? The WebGPU Dall-E and the WebGL sandwich shop shares the same kitchen. So why is the new one faster? It's because when you submitted your order in the front desk, they had time to translate it, reorganize your ingredients for optimal retrieval time, check for regulation compliance only once, only the first time you did it. It's more work upfront for you, sure, and that can feel annoying and overly intimidating at first, but now you are far less dependent on the driver or your waiter's clever skills in order to speed things up. Let's take a closer look at some of the core pieces of the API. This won't be comprehensive, but we'll touch on all the most important bits. We mentioned earlier, but it's still worth mentioning again, that WebGPU has its own shading language, which we'll call WGSL, pronounced Wixel. Honestly, we could spend an entire presentation just to comprehensively cover the shading language, so I'm not even going to try. Instead, we'll just pause here for a moment so you can get an idea what it looks like. The high-level important parts are that its syntax is somewhat Rust-like. It has the feature you'd expect for a shaded language in terms of vector or matrix math, swizzling, etc. And there are a few quirks due to it being both a young language and needing to wrap multiple different native languages. For example, pointer use is a currently topic of debate. I have found that I like working with it, though especially as it adds some more syntactic sugar during development. If you are more interested about learning about shading languages, there's an excellent talk at FOSDEM 2020 by Mozilla regarding usage of Rust in developing web GPU. You should probably have a look at that. We've already talked a little bit about pipelines, so I'm just going to skim over it here. Pipelines are explicitly either a compute pipeline or a render pipeline and serve as a way of selecting what shaders and shade you draw or dispatch commands will use. The queue also is part of the device which has a GPU queue. This is used to submit commands to the GPU and also has a handy helper function for writing to buffers and textures. When you begin a render pass, you give it information about the various attachments it will be outputting to, as well as how to handle loading and saving them. This is where clearing happens, as well as setting up multi-sample resolves for the end of the pass. Now let's tackle what's probably one of the trickiest parts of the WebGPU, bind groups. Coming from something like WebGL, this can seem really obtuse to work with, but the performance benefits can be significant if used well. How is it in WebGL? Well, this is so easy that it's insulting. It's not performant minding, but it is easy. Now, what happens in shader? Exposing resources to shader. When we try to expose the shader, we value the program coordination to a binding or a vertex attribute. For binding needs to be declared in two places. The first is in the shader itself, and here where we declare it. Now, these are each associated with a group and binding numbers of our choice. So this and this and this will be associated with a group. And these are the associations where it should be associated with. Now, next in JavaScript, you will create a corresponding GPU binding group layout for each group. It needs to match the resources definition in the shader which we just talked about. Now, if we look at it side by side with the corresponding shader, you can see that we have an entry for each binding in that relevant group. So we have a binding for each of the relevant group. So these are our bindings, and that each entry, so each of these entries describe a type of resources. So these are our type of resources that matches what the shader is expecting. Now, when you put it all together, once you have jumped through all of those hoops, drawing or dispatching is easy. Bind groups don't snapshot the contents of the resources, so updates to the underlying buffer textures are visible to the shader. Updating uniforms in WebGPU typically means creating a bind group with the uniform buffer once, then using the right buffer or similar to update the buffer every time. Looking at a simplified render loop, we can demonstrate a really effective pattern. If there is a set of resources uniforms that is used by everything that is being rendered, like camera uniform, then every pipeline you create should use the same bind group layout for the data. This allows you to set that data's bind group once at the top of the render pass, then never touch it again. Now, how WebGPU helps developers? Well, let's find a bug. This is the same hello triangle code which doesn't draw anything. Why? Well, in WebGL, debugging it mostly involves spamming your code with gl.getError. So, whatever you think the error was, then getting back one of the handful of enums that kind of node vaguely in direction of what you might be the problem. This is similar to Python's print statement. It's not really effective. I took this really as a personal challenge. Well, some of the tips for WebGPU, what we can do. An example of this in real world is that the developer of Doom Eternal, a well-performing Falcon game, has said the entire game uses 50 pipelines. This makes the case of minimizing the number of pipelines you use. Because the more pipelines you have, the more state switching and the less performance. It might not be trivial depending on where your assets come from. Creating a pipeline in advance pays dividend, just kind of like a sandwich shop. Because even though you can create a pipeline immediately before the work, just don't do it, because functions written immediately start work on a different thread. When you use it, the queue execution needs to wait for the pending pipeline creation to finish. This causes significant jam. Better use something like pipeline async, which depends on the promises to be resolved when the pipeline is ready to use without any stalling. Also, render bundles. We did talk about it a little bit. Render bundles are pre-recorded, partially usable render passes, kind of like modules. You can reuse it, you can replay that part of an actual render process later. Render bundles perform best when you have got something that you are drawing every frame that only varies by the contents of your bind group resources. These can be executed alongside regular render pass commands, and this pass rate is set to defaults before every bundle execution. Now, if you want to read some additional resources, you can go to these links. Some of the WebGPU samples, a tutorial. The raw WebGPU is an excellent tutorial to kind of learn about that, and some of the best practices we have talked in today's talk. Now, going to the other part of the talk, how to use the GPU, how to use it for generative AI, and those parts. So we're going to look at 10 ways of using machine learning in Google Cloud and how to use some of those models for on device. So it is kind of divided into 3 parts, 4 parts in beginner, some of them in intermediate, some in advanced. And we're going to look at all of them. So start with beginner. So Teachable Machine is a portal where you don't need to actually learn how to code or learn about machine learning. You can just get your data from webcam, microphone, or upload, and you can do different things on that. This is great for prototyping. These models are exportable, which you can then utilize in some web demos. For example, you do something with Postnet, you added some extra features, or you taught it to do something very specific. You export that module, you load it to a web page using WebGPU, and it's running completely on device, and you didn't have to code it at all. Auto machine learning, here you don't need any machine learning expertise. It is enterprise grade and high quality models are already available there. You can just go there, train your new transfer learning, and use them. Machine learning APIs for developers are available through Google Cloud. These are all industry-grade APIs. You can use vision, natural language, intelligence, and all these. At the latest, you also have access to generative APIs, which help you do like code completion or text generation. A generative AI Studio lets you play with LLMs, use prompts to generate images or text or summarize. And you can also tune the prompts and fine-tune the models. Let's look at what we have for intermediate. In intermediate, you have Vertex AI Model Garden. Here, it's a single environment that interacts with a variety of model types. The models span different modalities, and you can deploy them easily in any Vertex AI endpoint. There are 4 new foundational models in the model garden: the code generation and completion, also called CODE, which has been trained on the foundational model of POM 2. Then you have universal speech, MDings, which are interesting for all the LLM tasks, and image generation, like Imagine. The advanced part of this is that now you have tuning capabilities on top of that. So reinforcement learning from human feedback, or RLHF, is the same thing which OpenAI also used for its GPT 3.5, GPT 4, and it helps optimize machine learning model to performance with human feedback. It improves the pre-trained LLMs without increasing the model size, which is hugely beneficial. BigQuery machine learning also is there, where you can query directly your machine learning models directly with your data powerhouse. You also have Google Colab, which is awesome tool which gets you access to Google's free GPUs, and it lets you quickly prototype, build out on your ideas. And let's look at some of the advanced tools which are available. So Vertex AI Workbench is a Jupyter lab with fully customizable and customizable compute, where you can latch it to any of the GPU backends, and it is an enterprise-grade application. Vertex AI Custom Training allows you to have the same Jupyter lab and have enterprise-grade training available there, where you can do anything you want, export that model, export that as an API. Vertex AI Matching Engine is a fast scalable simulating search. It is a vector database for embedding, great for a variety of data modalities and enterprise grade. So these all are already available to you, which you can already use, export these models and use it for your own applications. All of these can be exported. Some of these models you can actually use here in your web applications, and WebGPU actually makes it much easier to have these kind of applications readily available. The example we had today, instability diffusion, that's not a one-off example. You can actually run other LLMs as well in a very similar way. They might not be the very good use case, but it shows the power of WebGPU you can have. Thank you. That's like what I had for today. If you want to keep in touch with me, if you have any questions, I will be here to answer that throughout the day, and I will be able to answer you. If you want to reach out to me, my LinkedIn profile is available in the part of the first slide in the QR code. You can also search by my first name @RABIMBA. That should be my Twitter name. And all of this should be available on my first slide. Thank you for having me. Thank you for visiting my talk. Have a good day.